We are following breaking news tonight as NASA confirms 3i Atlas is actively maneuvering. Scientists are scrambling for answers.
For years, the universe has followed a rhythm so precise that even its silence could be measured. Every orbit, every flare, every faint trace of motion has obeyed that ancient symmetry until now. Because somewhere beyond Mars, 3i Atlas broke formation. It didn't tumble, it didn't drift, it steered. Subtle, deliberate, and perfectly timed. Inside NASA, the anomaly appeared for less than a minute before vanishing from the public feed, replaced by static and revised coordinates. But NASA kept a copy, and the pattern they found wasn't random noise. It was control, and for the first time, space itself felt aware of us. When the Asteroid Terrestrial Impact Last Alert System, or ATLAS, flagged a faint, fast-moving object that the sun's gravity could not bind, astronomers realized they were witnessing only the third interstellar visitor ever recorded. Before it came Oumuamua in 2017 and Borisov in 2019, both of which behaved like uninvited guests passing politely through the solar system. But 3i Atlas, first detected on July 1st, 2025, announced itself with an energy that felt deliberate. Its incoming velocity exceeded 42 kilometers per second, its inclination slicing across the ecliptic at an angle no planet could have delivered. The initial orbit traced by JPL's Horizons database looked perfect, a hyperbolic path bending just enough around the sun before accelerating back toward deep interstellar space. For months, the model held true. Observatories from Hawaii to Chile confirmed each coordinate with clock-like precision. Then, approaching mid-October, that certainty began to splinter. On October 21 at 0012 UTC, the independent analysis collective known as Earth Exists reported that their telescope array had captured 3i Atlas several arc minutes away from its predicted position. Their measurement placed it at right ascension, 13 hours, 47 minutes, 54.3 seconds, declination negative 8 degrees, 21 minutes, 16.2 seconds. According to JPL's October 10 update, the object should have appeared at right ascension, 13 hours, 46 minutes, 57.5 seconds, declination negative 8 degrees, 15 minutes, 20 seconds. The offset, 15.4 arc minutes, translates to roughly 1.1 million kilometers of lateral displacement at a distance of 2.38 AU, almost 3 times the Earth-Moon span. That figure alone should have been impossible. Interstellar bodies follow gravity's script with merciless accuracy. Deviations of even a few hundred kilometers trigger reevaluation of every observation involved. Yet 3i Atlas's range reading remained exact. There was no misidentification, no parallax misfire, no optical noise. The telescopes were locked on the correct target, but the target itself seemed to have shifted sideways in defiance of celestial mechanics. Analysts proposed software desynchronization, clock drift, atmospheric distortion, every conventional excuse they could test. Each one failed. What remained was an object holding perfect distance while sliding across its predicted sky track faster than any known gravitational influence could permit. Somewhere in the cold between worlds, something had stopped following the rules. The first instinct among observers was to blame data, not physics. The 15.4 arc-minute gap, equivalent to 1.1 million kilometers at 2.38 astronomical units, was simply too large for comfort. Telescopes can misalign, coordinate systems can lag, even reference stars can drift if their catalogs aren't corrected for proper motion. The Earth Exists team ran every diagnostic possible. Star fields were remapped against the Gaia DR3 reference grid, atomic clocks synchronized through the network time protocol, calibration frames recalculated with dark and bias corrections. Every check confirmed the same truth. The numbers weren't lying. The image plane was solid, the timing perfect, and yet 3i Atlas continued to sit where no software predicted it should. In orbital terms, this wasn't just a curiosity, it was a contradiction. If the observing software had relied on outdated ephemerides from the previous quarter, the error should have leaned backward, placing the object slightly behind its projected course. That's what always happens when you use older orbital data. The object appears late because its velocity was underestimated or a minor gravitational influence went unmodeled. But 3I Atlas didn't lag, it led. The observed coordinates showed it ahead of schedule, several minutes farther along its trajectory than Newtonian mechanics would allow. To move into that position, something had to apply force perpendicular to its orbital vector, essentially a push sideways through space. At interstellar scales, lateral movement of even a few kilometers per second requires staggering energy. For an icy nucleus roughly the size of a mountain, there are only two natural mechanisms: asymmetric outgassing or gravitational assist. Neither matched the pattern. Its spectroscopic profile showed steady water and cyanogen release, no violent jets or rotational bursts that could generate thrust, and there were no nearby bodies large enough to tug it laterally. The only variable changing was the offset itself. By late October 21st, the discrepancy was already widening at 0.23 arc minutes per hour, a measurable acceleration that defied the static elegance of celestial motion. The equations described a comet, but the sky displayed intent. Each pixel shift hinted that the object wasn't merely drifting through sunlight and dust, it was steering, and for the first time since its discovery, the idea that 3I Atlas was under active control stopped sounding like science fiction and began to look like raw observation. In space, nothing just changes direction. Every motion, every drift, every captured orbit is the outcome of force and time, the clean math that keeps the cosmos from collapsing into chaos. But the readings from 3I Atlas began telling a story that didn't fit those rules. At first, the team thought it was a mistake, maybe a calibration slip or outdated software. Yet every test they ran said otherwise. The numbers weren't wrong, they were ahead. The comet was moving faster along its path than gravity allowed, as if it had quietly fired an invisible engine. Normally, when orbit predictions fail, scientists find a reason: a missing gravitational tug, a mistimed exposure, an error in the model. This time, nothing fit. JPL's Horizon system, updated less than 2 weeks earlier, showed a perfect trajectory. But when new observations came in on October 21st, the comet was already past the spot it was supposed to occupy. It wasn't lagging behind because of old data. It was leading, pulling away, carving through the sky on its own schedule. That single fact broke the logic of celestial motion. To gain a sideways velocity of nearly 4 kilometers per second, an object its size would need an impossible amount of energy, the kind of impulse that only propulsion could produce. Outgassing couldn't do it. The spectral lines showed no sudden bursts of vapor or jets strong enough to push it off course. And there were no planets or asteroids close enough to bend its path with gravity. The motion was smooth, stable, and deliberate, as though some internal process was guiding it. Then came another surprise. Within the reflected light were subtle distortions, tiny flickers that hinted at organized magnetic fields. Simulations showed that pattern only forms when ionized gases are being contained, not scattered, like plasma being shaped by electromagnetic loops. If that's true, then 3I Atlas isn't just moving differently, it's managing the space around it. Comets are supposed to brighten as they approach the sun. Heat wakes the ice, jets begin to vent, and sunlight scatters through the gas and dust, turning distant specks into streaks of fire. But 3I Atlas wasn't obeying that rule either. As its orbit pulled it closer, its magnitude didn't rise, it fell. The object grew steadily fainter, even though instruments confirmed it was venting more mass than before. For an object that should have been blazing brighter by the hour, the data made no sense at all. The expected reading from JPL Horizons listed its brightness at magnitude 14.83, but actual measurements showed 15.12, about 26% dimmer than predicted. The difference doesn't sound large, but in astronomical terms, that gap is enormous. It means the comet was reflecting only 3/4 of the light it should have, and that loss couldn't be explained by distance, angle, or instrument calibration. Something was either absorbing the light or redirecting it away from Earth. That idea drew quiet attention from engineers who'd once worked on plasma containment research. They noted that the same color spectrum, green, blue, and faint pink, wasn't random noise, but the signature of controlled ionization. Green from cyanogen, blue from nickel ions, pink from hydrogen collisions. It looked chemical at first until the color zones began appearing in clean geometric separations. Comets normally glow as chaotic spheres of dust and vapor, their light diffused and unshaped. But 3I Atlas was showing rings, edges, and symmetrical boundaries as though its gases were being confined within invisible lines. It didn't resemble natural outgassing. It looked organized. That idea was unsettling because it forced a question most scientists refused to ask out loud. If the dimming wasn't caused by random debris, could the object be managing its brightness intentionally, reducing visibility as it accelerated? It wasn't impossible, just unprecedented. The numbers matched the behavior of a ship trying not to be seen. When high-resolution images from the Chilean array came through, the team expected another faint smear of dust against the stars. Instead, they saw form, actual structure. Under single-frame enhancement, 3I Atlas revealed edges where no comet should have edges, shapes where only randomness should exist. Its nucleus didn't fade smoothly outward. It was divided into colored regions, sharp and deliberate, like the geometry of a manufactured object disguised as a celestial one. The outer halo glowed green, the signature of cyanogen molecules, a chemical common to many comets, but rarely so cleanly confined. Inside that, a blue ring pulsed with light from ionized nickel, and at the center burned a white-yellow core fringed with a pink directional glow. The colors weren't blending, they were separated, each layer holding its boundary as if electromagnetic walls were keeping them apart. To test for image artifacts, analysts compared the same field to two control bodies, the bright star Spica and Comet Swan R2, both in the same constellation. Spica appeared as a perfect circular point of white light. Swan displayed the usual cometary spread, irregular, diffuse, exactly as expected. But 3I Atlas didn't behave like either. Its symmetry wasn't optical distortion, and its gradients didn't match natural scattering models. The geometry persisted through multiple instruments, nights, and filters. Spectrographs taken during the same window showed something even stranger. The hydrogen line, normally the strongest signal in a comet, fluctuated with precise rhythm, as if being modulated. Those oscillations repeated every 4.3 seconds, a pattern no known rotation period or vent cycle could produce. It was too regular, too deliberate. When the data circulated through academic networks, the response was quiet disbelief. Many refused to comment at all. Those who did use cautious language, coherent plasma zones, non-thermal emission patterns, localized ion containment, words that admitted the truth without ever saying it outright. Whatever was happening near that nucleus, light itself was being engineered into order. Not long after the geometric images began circulating, a different set of instruments caught something no one expected. NASA's LASCO Solar Telescope, which monitors the sun's outer atmosphere, recorded a strange object passing through its field on October 20th. It appeared briefly, flickering with a cross-shaped burst of plasma, then vanished. Minutes later, it reappeared in another frame, smaller, sharper, then gone again. To most analysts, it was an optical ghost, the kind that happens when charged particles overwhelm the sensor. But when independent researcher David Sarita compared those frames to 3I Atlas's recorded position, the geometry matched almost perfectly. Same pattern, same timing, same direction of travel. When the images were processed side by side, Sarita's LASCO capture on one screen and the enhanced ground-based photo from Chile on another, the alignment was unmistakable. The luminous cross seen by LASCO overlapped with the structured color region seen from Earth. Two different instruments, one observing in visible light, the other in coronal wavelengths, had captured the same shape from opposite sides of the sun. If that was coincidence, it was a spectacular one. Then came another twist. Within hours of that solar observation, Earth's magnetometers began to spike. A G4 geomagnetic storm hit, the result of X-class solar flares released a day earlier. The storm knocked out radio signals across parts of North America and disrupted satellite telemetry for hours. It also flooded the upper atmosphere with electromagnetic interference strong enough to distort long-range telescopes. Most researchers assumed the flare and the comet's appearance were unrelated, but timing is a scientist's nightmare. And this timing was perfect. If 3I Atlas truly carried an electromagnetic field, even a faint one, such a storm would act like a jolt. Plasma structures could distort, brighten, or dim under that kind of solar impact. And that's exactly what the LASCO data showed. Pulses of intensity synchronized almost exactly with the flare's arrival. Some argued it was an artifact, a glitch of light and coincidence. Others quietly admitted that the correlation was too close to ignore. Every orbit has a turning point, the perihelion. The closest a body comes to the sun before being flung back into the dark. For 3I Atlas, that moment was calculated to arrive on October 25, 2025 at 11:36 UTC. Astronomers call it a simple gravitational milestone, but this one carried weight. On that date, from Earth's perspective, the comet would be directly behind the sun, invisible to every ground-based telescope, hidden in the solar glare for several days. In orbital mechanics, that's normal. In this case, it felt strategic. The geometry of that alignment was uncanny. As it slipped behind the sun, 3I Atlas would occupy a position that offered perfect cover for a major course correction. Spacecraft use similar windows. They hide their maneuvers when sunlight blinds the sensors watching them. The perihelion arc is also the most fuel-efficient time to change trajectory. The sun's pull amplifies any motion, requiring less energy to achieve more movement. For a natural object, it's simply orbital dynamics. For one that's maneuvering, it's opportunity. By the final week of October, the deviation from JPL's Horizon's path had grown large enough that predictive models no longer agreed. One projection showed the object curving slightly inward toward the sun's limb, another angled outward toward Venus's orbital plane. The actual position hovered somewhere in between, like it was choosing its own route in real time. Observers noted that its brightness kept falling even as solar radiation increased, a contradiction that made no physical sense. Every other comet brightens at perihelion. 3I Atlas was fading into the light as if it wanted to disappear exactly when the world couldn't look at it. When 3I Atlas vanished behind the sun, the world waited for its reappearance like an unanswered question. For 5 days, nothing came through. No optical signature, no thermal echo, not even background noise where it should have been. Yet the tracking algorithms running in observatories across Europe and Japan began to show faint irregularities in the data stream itself. It wasn't light they were seeing, but behavior. Numbers that should have been random were fluctuating in synchronized patterns, small oscillations that defied both instrumental error and statistical noise. Something about the absence was structured. It started with telemetry logs showing repeated calculation failures, not mechanical, but mathematical. Data packets from solar probes monitoring the region began returning with mirrored redundancy, like the same code was being written twice in slightly different ways. Error correction software tried to reconcile them and couldn't. Some called it a coincidence, others suspected interference. But one research team at ESA's Operations Center in Darmstadt noticed that the timing of these errors matched the last known vector of 3I Atlas to within fractions of a second. Whatever was causing the digital distortion was moving with it, unseen behind the sun. The deeper analysts dug, the stranger it became. Computational physicists studying the raw telemetry described the effect as non-causal. The system was returning solutions before the inputs were even complete, as if the computation itself were skipping ahead of time. One researcher compared it to quantum entanglement anomalies, where paired particles share states faster than light allows. The term that started appearing in encrypted discussion boards was entangled trajectory. No one dared to publish the idea formally, but the private notes circulated. The comet's position data was behaving like an algorithm running inside a larger computation, one that occasionally leaked into the networks, measuring it. It wasn't just defying gravity anymore, it was bending logic, showing patterns that implied feedback between its motion and the data used to observe it. By the time the sun's glare began to fade, the scientific consensus had fractured. Some said 3I Atlas had disintegrated. Others argued it had transitioned into a state beyond conventional detection. But those tracking the corrupted telemetry saw it differently. The object wasn't gone. It had simply changed the system that measured it. When the sun finally released its grip, the telescopes turned back to the coordinates where 3I Atlas should have reappeared. For hours, nothing. Then a signal blinked across the detectors, faint, displaced, and traveling along a trajectory no longer aligned with any known projection. Its position didn't match JPL's horizons, nor any of the predictive models built before perihelion. It was moving faster, dimmer, and slightly off-plane, like a ghost that had slipped out from behind the light. Whatever it had done behind the sun, it hadn't simply continued along its path. It had rewritten it. The final positional offset suggested a course correction of more than 2 million kilometers, a change too precise to dismiss as turbulence or coincidence. And still, its light remained subdued, stable, narrow, almost pulsed, as if its reflection was no longer diffuse but focused. Observers in Chile, Spain, and the Canary Islands compared notes. Each detected the same periodic dimming every 12.7 seconds, consistent with a controlled rotation rate or perhaps a signal. No one could prove it, but the synchronization was unnerving. For the scientific community, the implications were impossible to digest. If the deviations were natural, they represented physics we didn't yet understand. If they weren't, then humanity had just witnessed a kind of control that didn't belong to us. The official explanation was cautious. Unexpected, non-gravitational acceleration, a phrase that says everything and nothing at once. But the data left behind something more haunting, a pattern that looked engineered. In the days that followed, observatories cataloged the remaining frames, and then silence returned. The anomaly was gone, drifting back toward the outer darkness. No transmissions, no follow-up signals, no visible trace beyond the residual calculations that refused to balance. Imagine watching a single ember drift away from a distant fire on a windless night. You see its glow fade against the dark, its warmth still real but unreachable. Then, just before it disappears, it shifts sideways, pulsing once, like something alive inside the flame. 3I Atlas is that ember. Whether it cooled to ash or carried the spark of something greater, we may never know. But for now, the numbers still whisper the same message. The gap is widening, and something out there is steering.
A supposed comet is catching the attention of some of the nation's most renowned scientists.
Scientists are freaking out right now. An interstellar object called 3I Atlas was supposed to harmlessly pass by Mars, but it just did something that should be impossible. It changed course on its own. This isn't how space rocks behave. The thing is pulsing green light every 17 minutes like clockwork and steering itself with precision that defies physics. It's now on a direct collision path with Mars, moving faster than anything we've ever tracked from deep space. Is this really just a comet, or is something else controlling it? The discovery that shook astronomy. It began as a tiny blip on automated sky surveys, just another distant fuzzy spot among millions. But 3I Atlas has morphed from astronomical footnote into the most tantalizing mystery in our cosmic neighborhood. Detected on July 1st, this interstellar wanderer was initially projected to sail harmlessly past Mars. Now, In a twist that has left even veteran astronomers speechless, it's changed course, seemingly on purpose, and locked itself on a collision path with the red planet. This isn't how space rocks behave. Moving at a blistering 87 kilometers per second, 3I Atlas crosses distances that humble our human sense of scale. It devours the Earth-Moon gap in under 80 minutes, hurtling through space with a velocity no natural object should maintain after such a long journey between stars. More unsettling than its speed is its apparent defiance of basic physics. It's accelerating when it should be slowing, brightening when it should be stable, and making course corrections that seem calculated rather than random. Harvard astrophysicist Avi Loeb, once mocked for suggesting Oumuamua might be artificial, has stopped mincing words about 3I Atlas. His team's analysis reveals an object that doesn't just drift where gravity pulls it, it navigates with intention. The precision gas jets erupting from its surface mirror, spacecraft maneuvering, burns more than they do the chaotic outgassing of a typical comet. Each burst shifts its trajectory by fractions that across millions of kilometers have bent its path directly toward Mars. The astronomical community now faces a scenario straight from science fiction, an interstellar object roughly 400 meters across that appears to be steering itself toward a planetary rendezvous. If it strikes Mars at current velocity, the impact would reshape the planet's surface with explosive force millions of times greater than our largest nuclear weapons. The clock is ticking, with impact scenarios now projected for late September 2025, and humanity is scrambling to understand what exactly we're witnessing. From cosmic oddity to calculated approach. When 3I Atlas first appeared at the edge of our solar system, it looked refreshingly normal. Astronomers welcomed this third confirmed interstellar visitor as a chance to study pristine material from another star system without the bizarre properties that made Oumuamua so controversial. Early observations showed the expected fuzzy coma surrounding a small core with spectroscopic signatures suggesting familiar ices vaporizing in the increasing warmth of our sun. Throughout July, backyard stargazers and billion-dollar observatories alike trained their sights on the visitor. The European Southern Observatory captured high-resolution images showing what appeared to be a standard cometary nucleus surrounded by a growing cloud of sublimating gas and dust. NASA's automated planetary defense networks classified it as interesting but harmless, a cosmic tourist that would loop around our sun before being flung back into the endless night. Then came the first hint something wasn't right. The Mars Reconnaissance Orbiter, briefly pivoting from its study of the Martian surface to track our interstellar guest, captured a series of images that revealed rhythmic flares in the comet's brightness. Unlike the random flickering seen in rotating comets with uneven surfaces, 3I Atlas pulsed with metronomic precision, exactly once every 17 minutes, without variation. More concerning, each pulse coincided with a slight adjustment in trajectory, each nudge building upon the last. By early August, the pattern was unmistakable. The object wasn't just outgassing randomly as it rotated, it was releasing precisely timed jets of material in specific directions, each one steering it closer to Mars. The emissions followed no natural cycle, corresponded to no rotational period, and occurred regardless of the object's orientation toward the Sun. They appeared deliberate, with each burst perfectly calibrated to adjust course by exactly the amount needed to intersect the Martian orbit at a specific future time and place, breaking the laws of cometary physics. The mid-August data forced even the most skeptical scientists to confront an uncomfortable reality. The trajectory of 3I Atlas had changed significantly, not just the minor wobbles expected from normal cometary activity, but a wholesale redirection. NASA's Center for Near-Earth Object Studies confirmed a course change that should have been physically impossible through random outgassing alone. The object had altered its path by thousands of kilometers, precisely enough to transition from a distant Mars flyby to a potential impact scenario. The radar returns from deep space tracking stations provided the next shock. When powerful radio signals bounced off 3I Atlas, they revealed an internal structure unlike any comet ever studied. Instead of the expected weak, scattered returns indicating a porous jumble of ice and rock, the signals came back sharp and coherent, suggesting dense, organized materials beneath the fuzzy outer layer. The radar cross-section more closely resembled a metallic framework covered in ice than a natural cosmic snowball. Most perplexing is the energy problem. The thrust needed to make these course changes requires immense power, far more than solar heating could possibly generate at that distance from the sun. Each 17-minute pulse releases energy equivalent to several tons of high explosive, yet the object shows no signs of diminishing mass or slowing its burn rate. Something inside 3I Atlas is generating this energy continuously, like an engine, rather than the finite resource of sublimating ice that powers normal comets. Its current trajectory will bring it within 1.95 million kilometers of Mars on September 26, 2025, close enough for Martian gravity to exert significant influence. If the pattern of controlled burns continues, models predict the distance could shrink to under 50,000 kilometers. At that range, a minor velocity adjustment of just 10 kilometers per second, trivial compared to the burns already observed, would transform the close approach into a direct impact. The object is already accelerating when it should be decelerating, defying the basic thermodynamics that govern normal cometary behavior, beyond the realm of natural explanation. To grasp why 3I Atlas has shattered astronomical paradigms, consider how normal comets behave. These ancient ice balls drift through space until solar radiation warms their surfaces, causing frozen gases to vaporize directly into space. This creates pressure that pushes material away from the surface in random jets. These natural outbursts are inherently chaotic. They depend on surface composition, rotation, solar angle, and dozens of other variables that can't align with clock-like precision. Yet 3I Atlas defies this fundamental understanding. Its emissions occur exactly every 17 minutes, regardless of rotation, solar position, or any other variable. The jets emerge with surgical precision, not from random surface features, but from what appear to be fixed emission points that maintain their orientation relative to the target path rather than the object's physical structure. No known natural process can explain this level of regularity and directional control. The energy equation simply doesn't balance. The object is generating thrust that would require vaporizing tons of material with each pulse, yet its mass remains consistent. Spectrographic analysis shows emissions containing elements and compounds not typically found in comets, including traces of rare earth metals and isotope ratios that suggest either an origin around a very different type of star or artificial processing of materials. Most tellingly, the emissions contain short-lived radioactive isotopes that couldn't possibly have survived a journey between stars. They must be actively generated on board. The three-part structure of the tail defies conventional understanding as well. Normal cometary tails are shaped by solar radiation and the solar wind, forming a diffuse fan that points generally away from the sun. The tail of 3I Atlas splits into three distinct needle-like beams of coherent green light that maintain their geometry regardless of solar position. High-resolution imagery reveals these beams periodically adjust their angle and intensity in perfect synchronization with the object's course changes, suggesting they're functional components rather than passive emissions. Collision course consequences. If 3I Atlas maintains its current trajectory and purpose, Mars faces an unprecedented cosmic event. An impact would release energy equivalent to 2 million megatons of TNT, thousands of times more powerful than the largest nuclear weapon ever detonated. The resulting crater could stretch 60 kilometers across and burrow 5 kilometers deep, potentially exposing geological layers never before seen by our instruments. The Martian atmosphere, already thin, would be dramatically altered. The impact would vaporize surface materials and inject massive amounts of dust and gas into the atmosphere, potentially triggering a planet-wide dust storm lasting years. Some material would achieve escape velocity, creating a temporary debris ring around Mars, or even ejecting Martian rocks into interplanetary space, ironically making Earth a recipient of Martian meteorites in the decades to come. Mars currently hosts our largest off-Earth scientific presence. 7 active orbiters circle the planet, while Perseverance and Curiosity rovers explore the surface alongside the Ingenuity helicopter. These billion-dollar missions represent humanity's eyes and ears on our planetary neighbor. An impact of this magnitude puts this entire scientific infrastructure at risk, either through direct destruction, communication disruption from atmospheric effects, or damage from secondary impacts of ejected debris. The scientific implications spiral beyond physical destruction. If 3I Atlas contains engineered components, as the data increasingly suggests, an impact would scatter potentially recoverable technological artifacts across the Martian surface. Future missions could find themselves engaged in an archaeological excavation of extraterrestrial technology rather than geological exploration. If the object carries biological material, even dormant microorganisms, it could fundamentally alter the planet where we've spent decades searching for indigenous life, contaminating the very experiments designed to find it. Earth responds to the cosmic riddle. The unprecedented nature of 3I Atlas has catalyzed a global scientific mobilization unlike anything since the space race. NASA has diverted the James Webb Space Telescope from its scheduled deep field observations to focus on our mysterious visitor, using its infrared capabilities to peer through the cometary coma and map thermal patterns across the object's surface. These infrared images revealed the first evidence of the structured heat distribution that defies natural explanation, hotspots that remain fixed relative to the flight path rather than the rotating surface. The European Space Agency has shifted from scientific curiosity to active concern, upgrading 3I Atlas from object of interest to potential planetary impactor in their threat assessment protocol. Their Mars Express orbiter captured the first images of something even more puzzling: 3 small, highly reflective objects in high Mars orbit, arranged in a perfect equilateral triangle. Initially dismissed as imaging artifacts, multiple passes have confirmed these objects maintain their formation while orbiting Mars. Some speculate they could be advanced probes deployed during a previous approach, potentially mapping the planet for the incoming object. China's space agency has reprogrammed their Tianwen-1 Mars mission to prioritize tracking 3I Atlas, capturing the highest resolution images yet of the object's structure. These images first revealed the mechanical precision of the gas emissions, not random eruptions, but focused jets emerging from what appear to be controlled nozzles spaced evenly around the object's circumference. Meanwhile, Russia's network of radio telescopes has detected faint but consistent signal emissions from the object, not complex enough to contain meaningful data, but displaying artificial carrier wave characteristics impossible to explain through natural phenomena. Behind the public announcements, classified briefings have been held at the highest levels of government. Military space commands in several nations have quietly begun assessing whether any existing technology could intercept or redirect 3I Atlas if necessary. The calculations are sobering. Even our most powerful rockets would struggle to reach the object in time, and its mass would require nuclear options to significantly alter its course. For the first time, planetary defense concepts developed for Earth-threatening asteroids are being considered for protecting another world. The technological fingerprints. As more telescopes focus on 3I Atlas, the list of unexplainable features has grown from curious to convincing. The object's brightness has increased in stepwise fashion rather than the smooth curve expected as it approaches the Sun. Each brightness jump corresponds exactly to a maneuver sequence, as if additional systems are being activated in phases tied to mission stages rather than solar heating. Thermal mapping reveals an object that defies thermodynamic expectations. Instead of a gradually warming snowball, 3I Atlas displays precisely controlled temperature zone. The leading edge maintains a constant 120 degrees Celsius regardless of solar distance, while the trailing section remains at -50 degrees, a temperature differential that would instantly equalize in a natural object but remains stable over weeks of observation. 3 equidistant hotspots around the object's equator pulse, with energy output far exceeding what solar heating could provide at its current distance from the Sun. Spectroscopic analysis has identified chemical signatures that read like an engineer's material list rather than natural cosmic chemistry. Traces of titanium, beryllium, and specialized alloys appear in the emissions, materials ideal for spacecraft construction but vanishingly rare in natural comets. The isotope ratios of common elements like carbon and nitrogen don't match known stellar formation processes, suggesting either an origin around a truly exotic star or artificial processing and refinement. Most compelling are the radio emissions detected by the FAST telescope in China and confirmed by Arecibo in Puerto Rico. These signals maintain perfect frequency stability, a hallmark of artificial transmission, and pulse in patterns that correlate exactly with the object's maneuver timing. While not complex enough to contain language or code, they display characteristics of navigation beacons or synchronization signals rather than random cosmic noise. The signals intensify when the object executes course corrections, suggesting they may coordinate the precise timing of its maneuvering systems. The final approach window opens. As 3I Atlas continues its determined journey toward Mars, the scientific community braces for the critical approach phase beginning September 19th. This date marks the point when the object enters Mars's gravitational sphere of influence, the region where the planet's gravity becomes a significant factor in its trajectory. During this period, any final course adjustments would become immediately apparent, potentially confirming whether the object intends a flyby, orbital insertion, or impact. The 10-day window from September 19th to 30 represents humanity's last chance to observe 3I Atlas before its Martian encounter. Every major observatory on Earth has cancelled regular programming to focus exclusively on the object. NASA's Deep Space Network, normally responsible for communicating with our far-flung spacecraft, has devoted unprecedented bandwidth to radar mapping of 3I Atlas, creating real-time 3D models of the object as it makes its final approach. By September 19th, the object will have closed to within 500,000 kilometers of Mars's projected position, roughly the distance between Earth and the Moon. At this range, even small course adjustments become magnified, and the planet's gravity begins to bend the object's path. The sophisticated orbital mechanics at play will reveal whether 3I Atlas is using Mars gravity as a braking mechanism for orbital insertion, a slingshot for deeper solar system exploration, or an impact target. Space agencies have quietly begun preparing contingency plans for their Martian assets. NASA has uploaded emergency positioning commands to their rovers, directing them to capture imagery of the sky during critical approach window. Orbiters have been instructed to adjust their orbits to minimize exposure to potential debris while maintaining optimal observation position. If impact occurs, these instruments would witness a planetary collision of unprecedented scale, potentially the most significant astronomical event ever directly observed by human technology. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.